We are going to now take a look at bond energy and reactions, which is the last portion of our thermochemistry unit. So in energy transfer, we know that exothermic reactions are reactions that produce energy, okay? And these are things like combustion and cellular respiration or metabolism. And we have endothermic reactions, which require energy to go forward. And they are reactions such as photosynthesis or decomposition of water, anything like that. Now, in essence, we know from the previous unit in activation energy that bonded particles plus energy gives us separated particles, and separated particles plus gives us bonded particles, and energy. So we have these two basic reactions that we can kind of base what we know about bonds and our energy transfer in a chemical reaction. So bond energy is the energy required to break a chemical bond, okay, or it is the energy released when the bond is formed. So we're all talking about the formation or breaking of chemical energy bonds. So in an endothermic reaction, the overall change is endothermic. Therefore, the energy required to break the bonds must be greater than the energy released. So the energy required is greater than the energy released. So again, if you think about your diagrams, this is the energy required, would be your activation energy, and the energy released from those bonds formed is less than the energy required to put input into your reaction. So this is again your potential energy that we're looking at. In any endothermic reaction, more energy is needed to break the bonds in the reactants than is released by the bonds formed by the product. So again, that same statement just written in a different way. The energy released by these products is less so than the energy required to form those products in the reaction. Inversely, with an exothermic reaction, we have more energy released by bonds formed in the products than it's needed to break the bonds. Again, so if we think about our reaction potential, we have more energy released, we have a small amount of energy input, and again, more energy was released by the formation of these products than it was put in during our activation energy. So sufficient energy is initially added. Again, that's your activation energy, and this is light, heat, or electrical energy that is provided in order for this to happen in a forward direction. So in summary, we have a change in enthalpy represents the net effect, okay, so overall, from breaking and making bonds. So our change in enthalpy is the energy released from bond making minus the energy required for bond breaking. So in an exothermic reaction, making exceeds breaking, and your HR or your delta enthalpy is negative, and your endothermic reaction, your breaking exceeds making, therefore you have a positive change in enthalpy. Okay, so this is sort of consistent with what we've seen so far. Now, in fact, it's the same. It's all of these pieces that we've looked at so far are supporting ideas. So for example, in calorimetry, we've looked at a change in enthalpy that equals thermal energy. Now remember, we kind of called this enthalpy our potential energy, and this thermal energy Q. Okay, and Q, so this was change in enthalpy, is equal to EP, and Q we called was equal to EK. Okay, so we had this conservation of energy. Now in Hess's law, we said the change in enthalpy equals the sum of our component enthalpy changes. So this was very similar. We looked at anything that was from our products to our reactants, and we found the net or the sum of those enthalpy changes. Again, conservation of energy. In our molar enthalpies of formation, we looked at the enthalpies of formation of the products minus the reactants. Again, we're looking at conservation of energy here. And our bond energies, we look at the change in enthalpy equals the energy released from bond making minus the energy required for bond breaking. So again, we look at conservation of energy, and any energy released from bond making is going to be also subtracted from the energy required for bond breaking to look at our total energies. So we are always looking at a net enthalpy change, which is all based on the conservation of energy. Remember, we can't magically lose or disappear energy. We can change forms, but it's never destroyed. Okay? Now, just to finish up, we need to talk about catalysts. Now, catalysts are entities that are found all over in a variety of different areas of life. So we use them in industry, and essentially in industry we use them to create a more efficient system with whatever we might be working with. Now, in your body, we also have a ton of catalysts present. Now, in your body, most of the catalysts that we use in our bodies are enzymes. Now, enzymes, again, are an entity that cause a reaction to occur in just a more efficient way. And in your body, those catalysts or those enzymes can act at a specific temperature, which is pretty high because your body is generally at around 37 degrees Celsius, and it forces or allows a reaction to occur at that temperature, which is pretty cool. So a catalyst then is a substance that essentially just does that. It increases the rate of a chemical reaction, and it's not ever consumed. It is never part of the reaction. It just plays a role in guiding, you can call it guiding the reaction. Okay, so enzymes again are an example. Now, essentially, the purpose of these catalysts in a chemical reaction is they provide an alternative energy, which I'm going to do a capital E, energy pathway. That is the primary purpose of these catalysts. And we'll see in the next little bit here that this can potentially mean a variety of things. It's an alternative energy pathway, and it can be more simplistic or it can be more complex, but nonetheless, it increases the rate. We increases the speed and the efficiency of how that chemical reaction goes forward. So the chemical composition of our reactants and our products remain the same. Okay, they are the same as if this was to be an uncatalyzed reaction. Okay, this reduces the energy required to start that reaction. So this reduces our activation energy. Okay, we produce a greater yield in the same time period and temperature. So essentially, again, this is just increasing the rate, how much we produce in the same time period. Okay, we do not alter enthalpy. So our change in enthalpy is going to be the same regardless of if it's catalyzed or uncatalyzed. So it's this exact same. Now this is because we don't really consider time as part of our enthalpy reactions. We only consider the change in enthalpy, which remains the same. And this, again, they generally significantly increase the rate. Okay? So if I was to look at a diagram here of a catalyst and the effect of a catalyst on a reaction, this is an example of an exothermic reaction. We have our reactants and we have our products. Okay, we see that the net change is still negative. Initially, if we think of our analogy with rolling the ball up a hill, initially with an uncatalyzed reaction, we follow the orange pathway. Okay, we have to follow up and over this top of this hill to push the reaction in the forward direction. If we have a catalyst, we need less energy invested to push that ball over the edge of the hill. So essentially, we increase the rate because there needs to be less energy invested in this reaction, in the forward reaction. So notice, regardless if it's catalyzed or not, your potential energy is the same in both your reactants and your products. So let's erase some of this here. And we look at our reactants and our products, and it starts the same and ends the same in both the catalyzed and uncatalyzed. But this catalyst essentially just provides a pathway, a new pathway for this reaction to occur that is slightly more efficient in terms of time, the time that it would take for this reaction to occur. Now, again, it increases the reaction rate. It's not ever consumed in a reaction, and it just simply pushes it forward in a more effective manner. Now, this is sort of a simple catalyzed reaction. We have one just less activation energy. It's pretty simple to look at when we're looking at an effect of a catalyst. However, we may see some intermediates, and what I mean by intermediates is we may see a catalyzed reaction looking something more like this. Now again, we see that there's less energy for the activation energy, okay, but we do see, now my diagram isn't great because it's not computer generated, but we see that it could have little bumps in it. Now, if you remember, we called the top of this bubble, or the top of the crest of our hill, the activation complex. And essentially, that's just what is happening when your two reactants bump in together at the exact moment that they hit. Okay, so regardless of which crest of the hill we're talking about, it's both the activation complex. Now, what we see here is we kind of see 1, 2, 3 different crests of our hill. This means that there's some sort of intermediate reaction going on to get to our products. Now, again, this has no effect on our enthalpy change. We still go from our products to our reactants. There could be just a bunch of things in between. Now, again, we see this quite frequently with our enzymes. For example, in order to break down a protein, we use a couple enzymes like pepsin and pepsinogen to break down that protein, which means that there could be multiple intermediates to break it down into its smallest portion, being the amino acids. So just like in our body with breaking down proteins, we can do that with a chemical reaction of just about any kind. Now, this is seen, like I said, more in biological systems when we're dealing with enzymes, but essentially it would look something like this. We have intermediates produced, and they're varying stability, okay? So they have varying amounts of stability in this chemical reaction, but essentially you start with your reactants, you get your activated complex, so your two reactants have bumped together, and then that forms intermediate 1. Okay, and then intermediate 1 has an activated complex, again, probably 2 intermediates bump into each other, creating activated complex 2, providing us with intermediate 2. Now, intermediate 2, again, forms a new activated complex, intermediate 2 bumps into each other, and we have products formed. So your activated complex are all canceled out because these are just the entities that happen before you get any level of product. So I'm just going to put a little line through these guys because we don't really need to worry about them. You can't really see my line anyways, that's okay. And then with our intermediates, we can cancel anything on the far right with the far left. So I can cancel out this intermediate 1 with this intermediate 1 and this intermediate 2 with this intermediate 2. So we still get a net result of our reactants to our products. Again, meaning that our enthalpy will not be affected. And overall, this general process is maintained consistent. We go from reactants to our products. Now, again, I would definitely take a look to go over that bond energy and definitely be sure that you understand that catalysts do not affect that enthalpy. It just increases the rate of the enthalpy and provides a new pathway for that reaction to occur. That is really important to know, and it should be probably brought up on a diploma. If you need to go back and take some additional notes, I would suggest doing that now, and good luck.